Hi, so this video is over section 3.4, which talks about measures of position and also outliers. Um, so what we're going to start with talking about first is this idea of z-scores, right? That's learning objective 1. So we want to determine and interpret z-scores. So the z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data value and dividing the result by the standard deviation. So there is both a population z-score and a sample z-score. And you can see below, we use the same symbol for the z-score if it's population or sample, right? But notice the different mean and standard deviation values that we've been using the entire time. Right, so if we look at the top, right, we're taking the data value minus the mean. So here we're calculating the distance from the mean in the top, and then we're dividing by the standard deviation in the bottom. So that will turn my units into how many standard deviations I am away from the mean. Right. So if we go back to a diagram that we looked at in the last section, when we looked at the empirical rule, right, we have here, remember this is also referred to as the 68, 95, 99.7 rule, right, or the empirical rule. Right, so if we're looking at this diagram, what I could do is I could make another axis right below this one, and then right in the center is the mean. So this new axis I'm going to call this the z-axis, right? So when you're at the mean, the z-score is 0, right, when you're at the mean. And then when you go one standard deviation to the right, that's a z-score of 1, right? And then if I go another standard deviation to the right, so that's total of 2 standard deviations to the right, then that's a z-score of 2. And then this would be 3, right? So the z-score tells you how many standard deviations you go away from the mean. If we go to the left, 1 standard deviation, right? This is like minus 1 standard deviation. This would match up with a z-score of -1. If I go another standard deviation to the left, this would match up to a z-score of -2. And then if I go another one, that would match up with a z-score of -3. Right? So the z-score tells me how many standard deviations I am away from the mean. So something else to keep in mind is depending on your data set, you're going to have different standard deviations, right? So that standard deviation, that unit, is going to change. But the idea is I go 1 standard deviation to the right or the left, that's going to match up with those same z-scores. Right? So I have an example. So z-scores are really helpful. Really helpful when you're comparing numbers from different distributions. So this example, we're comparing upper arm length of a 19-year-old male to an upper arm length of a 19-year-old female. So it's not really a fair comparison to compare male to female, because generally speaking, males are taller than females, and your upper arm length is typically correlated with your height, right? So an upper arm length for the male is most likely going to be bigger than an upper arm length for a female. So it's not a real fair comparison. So what we do is we can calculate the z-scores for each. So in other words, I'm going to compare the male's upper forearm to all the males, and the female's upper arm to all the females, and see which one's more abnormal, right, or more atypical, if you will. So we're going to call that, we're saying which one's relatively longer. You can see in the question, right? So here, who has the relatively longer upper arm length? And this might not seem as obvious why you have two different distributions. Maybe a more obvious one is if you were comparing ACT scores to SAT scores, right? So the score range for SAT, I believe, is 200 to 800, where the mean's around 500, while the mean ACT score is 21, and the score ranges from like 1 to 36. So if I wanted to compare someone who took the ACT to the SAT, it's not really fair just to compare their score values because they're completely different distributions, right? But if we were able to compute the z-scores for each, that would be a better way to compare those. So z-scores are best to compare things from different distributions. Right, so I'm just going to copy down the information that we have from the reading from the problem. So um, we're told that the mean for the males is 38.6 centimeters. We're told that the standard deviation for the males is 2.9 centimeters. And then the x value, the data value from the males that we're looking at, is 41.1 centimeters. Right? And then for the females, we know the mean for the females was 35.8 centimeters. The standard deviation for the females is 2.8 centimeters. The x value from the females was 38.4 centimeters. Right? So to calculate the z-score for the males, we would take the x value of the male minus the mean from the male divided by the standard deviation of the male. So plugging that in, we would have 41.1 centimeters minus 38.6 centimeters divided by 2.9 centimeters. So if I simplify the numerator, we get 2.5 centimeters divided by 2.9 centimeters. And then so here, you'll notice I have centimeters on the top and bottom, so those cancel out. So what we're left with is a unitless measurement. Right, so if you take 2.5 divided by 2.9, you get approximately 0.862. Right, so this is unitless. Right, so then we need to compute the same thing for the females. So the z-score for the females would be equal to the x-score of the female minus the mean from the female divided by the standard deviation from the female. So plugging these values in, I would have 38.4 minus 35.8. These are both in centimeters. And then divide that by 2.8 centimeters. So then on the top I get 2.6 centimeters divided by 2.8 centimeters. So same thing, the centimeters cancel out. So we're left with a unitless measurement, and that comes out to be approximately 0.929. So you can see that the z-score of the female was greater than the z-score of the male, right? So we could say that the female has a relatively longer upper arm. Right. So if you wanted to visualize this, I can come down here, draw a normal distribution. So right in the center of the curve, I'll let this be z-scores. This would match up to be 0, right? And then we're going to have 1, 2, and 3 on here, -1, -2, -3, and so forth. And then, I could draw another axis, maybe for the males, right? So what would go right here, match up with 0, would be the mean from the males, which was 38.6 centimeters, right? And then what would match up here is I'm going to be adding 1 standard deviation to the 38.6, right? So the standard deviation for the male is 2.9 centimeters, right? So I'm adding 2.9 centimeters to find that tick mark, that value. So if I take 38.6 plus 2.9, we get 41.5, right? And then to find the next value matching up with the 2, I would take 41.5 and add 2.9 to it, right? Because I'm going one more standard deviation. So that's 44.4. And then lastly, matching up with the 3, I would take 44.4 and add 2.9 to get 47.3 centimeters. Right, and then if I wanted to find these values that match up with a z-score of -1, -2, -3, I need to subtract 2.9, right? So I would take 38.6 minus 2.9, we get 35.7, minus 2.9 again, we get 32.8, and then do that again, minus 2.9, we get 29.9. Right, so now I can draw another axis. I'll call for the females. So again, what would go directly in the middle, lining up with a z-score of 0, would be the mean. So the mean for the females was 35.8 centimeters. Right, and now this is different because I'm going to go 1 standard deviation to the right again for the females, but the value of the standard deviation is different, right? This is 2.8 centimeters. So I'm going to take 35.8 plus 2.8 to get 38.6. And then going here, I'm going to add 2.8 again, right? So take 38.6 plus 2.8. We get 41.4, and then add 2.8 again. We get 44.2, right? And then going this direction, I would subtract 2.8. So we get 35.8 minus 2.8. We get 33 minus 2.8 again. Get 30.2, and then minus 2.8 again. Get 27.4. Right, so all, so in other words, like these values are comparable to one another, the male and the female, right? Because they both match up with 3 standard deviations to the left of the mean. So if I mark where I was, so the male value we were looking at was 41.1 centimeters. So that would be, somewhere around here. And then for the female, we were at 38.4. So that'd be somewhere around here, right? And then what we did is we crosswalked it up to specific z-scores right on the z-axis. So this was the z of the male, which was approximately 0.862, and this mark here would be the z of the female, which was approximately 0.929. Right, so you can see the z-score for the female then is greater than z-score for the male. Right? All right, so the next concept to look at are percentiles. So the kth percentile is denoted by P sub k of a set of data is a value such that k% of the observations are less than or equal to the value, right? So you can see here we have like a table. So if you look at p sub 1, there's going to be just 1% below you, right? So that's the bottom 1%, where p sub 2, right, lines up with the bottom 2% and so forth. So if you look at like p sub 98, it means there's 98% to the left of you or below you. So in other words, you're in the top 2%. P sub 99 means that 99% is below you, or you're in the top 1%, right? So maybe you've dealt with percentiles if you have a child and have taken them to the doctor, or maybe if you went to the doctor yourself. You know, it's often told of you of small children is their percentile in height, weight, and head circumference. So, for example, if your child was 90 percentile in height, that means that for your child's gender and age group, he or she is taller than 90% of the kids in that grouping, right, of that age and gender. Right. So another common use of percentiles is when you take like a standardized test, right? So like here, this is an example of someone taking the GRE, which is a graduate record exam. So it's a typical test taken in order to get into a master's program or a doctoral program. So it says here the GRE is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than 70th percentile for admissions into their Human Genetics MPH or MS program. And we're asked to interpret this admission requirement, right? So if you first, just try to show this in symbols, right, just to kind of grasp this, you're going to want your GRE score to be greater than or equal to the 70th percentile, right? So in other words, one interpretation that you could say is, to be admitted to the Human Genetics MPH or MS program, you need to test into the top 30% on the GRE, right? So I turn this around to say top 30%, because that would mean the same thing, right? So, if you're in the 70th percentile, it means you're in the top 30%. So it's kind of like glass half full, half empty kind of thing. I think focusing on being in the top 30% makes it easier to interpret and understand, right? So in other words, you would be like if there were 100 people taking the test, right? You would be the 70th or higher person, right? If you lined everyone in order from lowest test score to highest test score, right? So then the next thing we want to talk about are quartiles, which are specific percentiles. So a quartile, like a quarter, you're dividing things into fourths, right? So like there's 4 quarters in a dollar, right? It divides a dollar into 4 equal parts. A quartile is going to divide your data into 4 equal parts. So, you can see here, quartile 1, that's going to be like the 25th percentile. Quartile 2, which is the median, is like the 50th percentile. Q sub 3 is going to be like the 75th percentile, right? So these quartiles are what we're going to be talking about and finding, right? So you can see that they break the data into 4 equal parts, right? So in order to find a quartile, essentially what you're going to do is arrange the data in ascending order, smallest to biggest, and then you're going to find the median, and then you're going, this median is going to divide the data set into 2 halves. So the observations to the left of the median, the observations to the right So then you find the median of each of those lower halves essentially, right? To find Q1 and Q3. So let's practice that with this example. Um, so this is a data set that we've been working with a lot. It's the commute time, travel time in minutes to work for all 7 employees of a startup web company. Right? So the very first thing we want to do is put this in order from smallest to biggest, which we've worked with this data set a few times and done this. Let's see, this is 43. Right? We've actually already found the median of this data set too, right? The middle value, which is here, this is the median. So then, like I was saying, this data is split into 2 halves now. So this is like the bottom half. And this is like the top half. So you're going to find the median of each of these halves. So the median for here out of 3 numbers would be here at number 18, so that's quartile 1. And then the median of this top half would be 36, which would be quartile 3. Right, so we're just finding the medians of each of those lower halves. Right, so Q1 is equal to 18. The median, which is equal to quartile 2, is 23. And quartile 3 is 36. Right. So I'll show you now, going into StatCrunch. Right, and I'll just label the variable commute, and then I can fill these numbers in. So we had 23, 36, 23, 18, 5, 26, 43. And I can hit summary stats column, and then select my variable. And I'm interested in Q1. Oops, let me go over here. I'm interested in Q1, and then the median, and Q3. Hit compute, and those are those three values that we just got. Right, so that's how you can find it with StatCrunch. Right, so then the next example is finding quartiles, but we want to use StatCrunch to do this. So in other words, it's going to be a really large data set, like more practical, where it's not real easy to do this by hand. So I'm not going to use this data set that's listed here. I'm going to use a data set that we've used before with the Chicago salaries. So Chicago underscore salaries .csv, and that's on modules in the data sets. So the variable we're not going to use is our ROI, return on investment. We're going to use the annual salaries. Right. All right, so I'm going to go in and just click data sets from my textbook. This was, I think, in chapter 3. And there's Chicago salaries, right? And if you don't want to open it up this way, that's just one way. Remember, I put the actual Excel file on Canvas modules underneath the datasets module. Right. So we want same thing. Go to summary stats and column. We're looking at the annual salary variable, and we want to calculate Q1, the median, and Q3. Hit compute, and we can get those values. And then we can report those on the notes, right? So we're stating what they are, but also interpreting them. So Q1 was equal to 76,266, right? So an interpretation of this, we could say that 25% of Chicago public employees make less than or equal to $76,266 per year. Right, so then the median, which was quartile 2, is equal to 90,024. So this would be very similar. The only thing I would change would be the parts I put in this box, right? Just these numbers would change. Right, so this would be 50%. 50% of Chicago public employees make less than or equal to $90,024 per year. And then quartile 3 is equal to 96,060. So again, the only thing that will change are the values in these boxes. So this would be 75% of Chicago public employees make less than or equal to $96,060 per year. Right. So then the next thing we want to look at is called the interquartile range, the IQR. So that is the range of the middle 50% of the observations. Right, so what we mean by that is we're going to take the difference between the third and the first quartiles to calculate that, right? So like if you go up here to this diagram, the interquartile range is the difference between these two things. That's the interquartile range. So what we want to do here is to find and interpret the interquartile range from either of the finding quartiles example. So I'm going to use the Chicago salaries example. All right, so the IQR interquartile range is equal to Q3 minus Q1, which in that case is 96,060 minus 76,266. That difference is $19,794. So then we want to find and interpret that. So we could say the range of the middle 50% of the Chicago salaries data is $19,794. All right, so then the next part of this on the top of the next page is a summary of which measures to report. So one thing that's going to be a common theme in statistics is one thing you want to start with is look at a picture. Right. So before you calculate a measure of central tendency, which we can also call this like a typical value, and versus a measure of dispersion, which is like the spread, horizontal spread. What we're looking at, so before you calculate those values, what you want to look at is the shape of the distribution to see what's appropriate, right? So if you have a symmetrical distribution, we looked at it's appropriate to calculate the mean and the standard deviation for the measure of central tendency and the measure of dispersion. But if you have a distribution that's skewed left or skewed right, remember in the last section we looked at how the mean is impacted a lot by just one single like extreme value. So you're going to want to use the median for a measure of central tendency if something's skewed left or skewed right. And then the standard deviation, the formula for that's based on the mean. So it makes sense that we need something else for measure of dispersion for something skewed left or skewed right. So it turns out the interquartile range is what we report there. And you can see how that's related or similar to the median, right? Because we're finding the quartiles to find that. So that's important to remember. Something else that I want to mention is if you're comparing two distributions, you could have some different situations. So for example, one situation is that you could be in a situation where both are symmetrical. So in that case, if they're both symmetrical, of course you would just look at their mean and standard deviation, right, of both and compare those apples to apples, right? The second scenario is that they could both be skewed. If they're both skewed, you would do the median and IQR, right? Then the third scenario is you have, one that's symmetrical and one that's skewed, right? In that case, you would go with the median and IQR, right? So if you have at least one of the distributions skewed, you're going to use the median IQR to compare those. But both are symmetrical, you would calculate the mean and standard deviation, right? So that's if you want to compare measures of central tendency between two different distributions or two different measures of dispersion, right? So then the last learning objective in this section is being able to check a set of data for outliers. So there's not, one set definition for outliers. This is one standard way to calculate outliers using the interquartile range in quartile 1 and quartile 3. So extreme observations we call outliers. And, these can occur by chance. They can occur by error in the measurement of a variable, maybe during data entry or from errors in sampling, right? So they could come from error or they could just happen naturally from chance. So in order to calculate outliers, you have to do the following, right? You're going to calculate quartile 1 and quartile 3, calculate your IQR, and then you're going to find what are called these fences. And these fences serve as cutoff points for determining outliers. So we have a lower fence, which is quartile 1 minus 1.5 times the interquartile range. And then we have an upper fence, which is found by taking quartile 3 and adding 1.5 times the interquartile range. And then if we have a value that's less than the lower fence or bigger than the upper fence, then it's considered an outlier. Right, so in other words, if you want like a diagram, here is going to be my lower fence. Here's my upper fence. So anything inside of here is good. And then anything outside of here would be an outlier. Right, so if you're outside of those two values, you'd be an outlier. So what we're asked to do here is to check the data from either finding quartiles. I'm going to use the Chicago salaries again to check to see if there's any outliers. So quartile 1 is equal to 76,266. Quartile 3 was 96,060. And the interquartile range was 19,794. Right, so these are all values that we've calculated. So we need to find the lower fence and the upper fence. So the lower fence is Q1 minus 1.5 times the interquartile range, which would be equal to 76,266 minus 1.5 times 19,794. 794. So if you plug that in the calculator, you should get 46,575. The upper fence is quartile 3 plus 1.5 times the interquartile range, right, which is 96,060 plus 1.5 times 19,794. So again, plug that in a calculator, you should get 125,751. And then if I look at the min and the max values from this data set, the min is 12,840 and the max is 300,000. So it's clear that I definitely have outliers to both sides, on the left and the right of the data, right? Because my min, I have at least one value that's smaller than this 46,000, right? We have at least this min number, and this 300,000 is bigger than this. So we're going to have at least one outlier on either side. So if I go to my stat crunch, right? If I wanted, I could go to options and edit and add some other things here. So like if you wanted to add like the interquartile range and the min and max, hit compute. So you can find all of those, the min and max value just reported and the IQR. And then if I go here and go to sort the table ascending, you can see there's a whole bunch of values less than the lower fence, which was 46,575, right? So it looks to be hundreds, over 100 values there. And then if I sort the table descending, so look at the biggest to smallest, you're going to see there's a whole bunch of values bigger than 125,000 as well, right? So we have a lot of outliers in this data set. So in this case, looking at this, there's so if I go to options and go to edit, I'm going to add in the n value to my table. So the n value tells me, so there's 25,159 people in this data set, right? That's a lot. And there's various different job titles and different departments. So maybe it makes sense to break those out a little differently, or like add in another variable like years of service, education level, those kind of things. It's a lot of different jobs, so that's probably why we have a lot of outliers here. All right, so that's all I have for this section. Let me know if you have any questions. Thanks.